Hi everyone, my name is Amanda Karakas and I'm going to be giving you two lectures on AGB stars, asymptotic giant branch stars, and the S process, so slow neutron capture process. And I was originally asked to give a lecture only on the S process, so 2.5 hours on the S process. But since the main site of the S process is AGB stars, I thought I will break it up into two lectures. And the first lecture, so the lectures will cover the following two topics. The first will focus primarily on the stars that make the S process elements. And we will focus on the evolution and the nucleosynthesis that occurs inside AGB stars. The second lecture will be on the S process, where it occurs in nature, how it occurs, and then we'll end with a little discussion about galactic chemical evolution. However, so the first lecture here is, there'll be an introduction. I will discuss some basic stellar evolution because I think there will be a range of backgrounds of students attending this school. So some of you will have stronger nuclear physics backgrounds, and likely some of you will have stronger astrophysics backgrounds. So just to make sure we're all on the same page, I will start with basic stellar evolution and then look at the details of evolution and nucleosynthesis, because the two are intimately connected. So we'll look at the evolution and nucleosynthesis of AGB stars of varying mass, and that will lead us into lecture 2, which will be on the S process. Okay, so let's start. So, broad introduction. 13.7 billion years ago, the Big Bang occurred. Now, the Big Bang did not make elements heavier than lithium, primarily hydrogen and helium, and a little bit of other things. A little bit of lithium-7, a trace of deuterium, and a trace of helium, although these are part of hydrogen and helium, of course. Everything else that we see, everything else, I guess most of really what makes up this planet, which is not hydrogen and helium, and a lot that makes up us, was made inside a giant stellar furnace, a star. So that we want to ask the question, what stars produce what elements? Our sun, of course, is a star, and it's somewhere in the middle of its main sequence life. But what will happen to it when it ages? Will it make elements deep in its interior? And if so, how will they get into the interstellar medium? So this lecture will be focused on low and intermediate mass stars. I briefly discussed massive stars in the lecture on the S process because they are one of the sites, but here the focus is really stars between 0.8 to about 8 solar masses, although these mass ranges, of course, are greatly dependent on input physics, such as initial composition, and even numerical methods used in theoretical models. So this shows a diagram where we have mass on the x-axis increasing and evolutionary phase increasing on the y-axis. Now, the stars that we're most concerned about, they have lives that are they live and die within the age of the universe. That sets a lower bound for the initial mass at about 0.8 solar mass. So these stars, as you can see, they go through core hydrogen burning. They go through a phase of core helium burning before ascending the asymptotic giant branch. During this phase, which is very brief in terms of previous evolution, they experience nucleosynthesis, including S process element production. Afterwards, they will lose their envelopes to become carbon-oxygen white dwarfs. There is also a range that I'll consider briefly, and these stars are a little bit more massive, say 7 to about 10 solar mass initially. They also go through core hydrogen and helium fusion burning stages, but then they may also experience carbon ignition as well. So they enter the AGB, they still go through an AGB phase, but this time they have more massive cores. The composition of their cores might be now oxygen and neon, not carbon and oxygen. We call these super AGB stars. And I'll briefly discuss super AGB stars. So just some definitions. I've highlighted in red the stars I will mostly focus on. These are our low mass stars, intermediate mass stars. I will briefly discuss super AGB and mention that some of these stars may explode as electron capture supernovae, and I won't really discuss massive stars in this lecture at all. So you'll see that there's these mass ranges. They're not arbitrary. They correspond to important evolutionary stages, essentially, or they correspond to a way a star does something. So you'll notice the low mass range is between 0.8 to 2.2. This is not arbitrary. That 2.2 is the maximum mass for a star to experience what we call the core helium flash. So this is the way the star ignites core helium at the tip of the red giant branch. There is also the maximum mass for an intermediate mass star, which is about 7 solar mass. And this is the maximum mass for making a carbon-oxygen white dwarf. Stars more massive will go through carbon burning and they will do different things. Now, all of these definitions are for models, theoretical models of solar composition, and I will discuss abundances briefly as an introduction, but that's roughly where the global mass fraction is about 2%. And they're also for models that don't have any, and I'm not going to go into the details of stellar modelling, but these are for models that don't have any what we call convective overshoot during the main sequence. And if you have convective overshoot, these mass ranges will shift down by a bit. So instead of 2.2, you might have 1.8 solar mass for the limit of a low mass star. Hopefully that's already introduced some of the uncertainties. Okay, let's continue with the introduction. There is a wonderful table of elements here, and this is the periodic table. Historically, the astronomer's view was very simplistic, where we considered the mass fractions of hydrogen, helium, and everything else. And we've labelled that everything else to be the global metallicity. So we've labelled everything that's not hydrogen and helium metals. Historically, that's because it was really quite straightforward to make a stellar model of a star with just hydrogen and helium and everything else. However, we know that there's a wonderful world of elements out there and isotopes. So if we want to model them in more detail, we need to have more detailed theoretical models, and that is what we generally have today. Okay. So when we talk about Sprocess, I'm going to, I guess, even though this lecture is about AGB stars and their nucleosynthesis, I do want to focus a little bit on essentially the stars that make elements, because there are, for example, stars less than about 0.8. They may eventually go through an AGB phase, so they may experience some of the same evolutionary features I'll discuss here in this first lecture. But these very low mass stars, they live so long, their main sequence lifetimes are so long that they are still fusing, that even the very first 0.8 solar mass stars are more or less still fusing hydrogen in their course. They haven't evolved beyond the main sequence. So these stars have not contributed to this story of the chemical evolution of our galaxy. And by that I mean these are stars that have lived and died since the universe formed. They've released, either they've exploded as supernovae, or they've released their winds if they're lower mass stars, and they've produced fresh elements. But these low mass stars haven't done that. So we consider them useless from the point of view of chemical evolution, but we use them as traces of chemical evolution. So their compositions essentially retain the place and time of their birth. So they're really useful to trace the processes of how elements have evolved in time. In terms of the stars that are the most useful, we talk about massive stars that explode as core collapse supernovae, so type 2 supernova. The low and intermediate mass stars that are the main focus of my lecture here, and as well explosive events involving binary evolution. such as type 1a supernovae, emerging neutron stars, and novae. Okay, so obviously if you have an explosion, how you get material from inside the star into the interstellar medium is really obvious. You explode it and it gets out. You will end up with a supernova remnant, such as shown on the right-hand image. What if you have a low mass star? How does that happen? Well, it's a bit different. There's no explosion, but what we have instead is mixing. So you have nucleosynthesis take place in the very central regions of the star, and then there's mixing between the core and the envelope that dredges up some of that material and mixes it into the envelope. Then winds, outflows, remove this material into the interstellar medium. And so there's different ways of then getting products, freshly made elements into the galaxy. So this is just a summary, putting in words what I've just said. So we need a way of mixing processed material into the ISM, interstellar medium. And I've just highlighted with low and intermediate mass stars, there is no explosion, especially if they're single stars. And I won't discuss binaries for the reasons of time and complexity. But generally, we have mixing between the core and envelope, and then combined with mass loss or outflows that removes that material into the interstellar medium. Okay, what about birth masses? And this really comes down to one of the reasons that low and intermediate mass stars are important from the purposes of producing elements, and in particular why they are an important source of the slow neutron capture process. And it comes down to the distribution of birth masses in galaxies. This is a slide I took from Frank Timmis's website, and I like it because it shows a rough breakdown of how many stars are born. If you have a pie chart and you break it up, we find that 90% of stars are what I have labelled very low mass stars, so less than 0.8 solar mass. So that means that if you take 100 stars, 90 of them, more or less, are going to be stars less than 0.8, M-dwarf stars, much like Proxima Centauri, our closest neighbour. About 10 of those stars will be intermediate mass stars, and here these are my low and intermediate mass. So these are stars that will go through an AGB phase, but for massive stars, now we have to think about larger statistics. So let's say so here Frank has broken it up into 10,000 low mass stars, we have 1,000 intermediate mass stars, and there's one massive star in all of that. So the massive stars are very rare in comparison to the total number of stars that are born in the galaxy. Low and intermediate mass stars are also rare. They're rarer than our M dwarfs, but there are many more of them. And indeed, if we are to add up, and this is an exercise I won't do, but you could try doing, take a salpeter initial mass function, which is something that is a power law that is a very simple power law that explains how stars are born, the number of stars per unit mass. And you can estimate the number of stars, and you can see in a certain mass range. And then you can convert that into mass and how much mass is born in a certain mass range. You see that by number, there's many more AGB stars. But when you consider it by mass, it's not quite as bad. It's not still favoured in terms of supernovae, but it becomes a bit more, it becomes less, I guess, what's the word? Less extreme, I guess, the ratio between them. Okay, how long do stars live? This is just a quick summary table. Again, I've highlighted in grey the massive stars. I'm not going to focus again too much on those, but just to highlight, they have very short lifetimes. According to the age of a galaxy, they're essentially instantaneous. Low mass stars, however, and intermediate mass stars, they really range, they span all low, so let me start again. All massive stars have short lifetimes. By the age of the galaxy, they're instantaneous. Whereas low and intermediate mass stars, we're talking about a range that goes from 8 solar mass, which are much more like has a lifetime much more like a massive star, very short. But then we drop down by many orders of magnitude. If we drop down, so we drop down in mass, but by say an order of magnitude, but we increase the stellar lifetime by many orders of magnitude. So you see a 1 solar mass star in comparison lives for 10 billion years compared to say only 30 million years for an 8 solar mass star. So the difference, so really our low and intermediate mass stars span everything from essentially almost instantaneous lifetimes compared to the age of galaxies to objects that have lifetimes of the same age as our Milky Way galaxy. I just want to give you a quick note on stellar abundances because I will present some results from stellar abundance work, and it's hopefully, again, this is something that you may not be familiar with. So generally, theoretically, we use the concept of mass fraction. So for example, 70%, if I were to add up the amount of mass in the sun and the fraction of it that's hydrogen, and let's say I divide that mass of hydrogen by the total mass, it's the mass fraction of hydrogen. Let's say that's 70%. We can do this with helium and our metal content, which we call the global metallicity. And I've put some example numbers for the sun. Most of the Z, this is the global metallicity, is in the form of CNO nuclei. That's carbon, nitrogen, and oxygen. And most of that is carbon 12, nitrogen 14, and oxygen 16. You add that up, and that's about 65% of the global metallicity is in the form of carbon, nitrogen, oxygen. And indeed, 42% of that is in the form of oxygen. Let's see. We also sometimes refer to abundance by number. That's generally where we take the mass fraction and divide it by the atomic mass to get, sometimes it's called a mole fraction. From observations, abundances have a different notation. Often they're given in what we call stellar spectroscopic notation. So I've given the common notation in the two red equations. The first one is sometimes log epsilon or A notation, where you have the number abundance of some element divided by the number abundance of hydrogen. Then there's a square bracket notation, where you might have the ratio of two elements in square brackets. This is really just a number ratio in, for example, of X and Y in a star, and you divide that by that ratio in the sun, and you take log 10 of that. Now, often you'll see iron to hydrogen in square brackets. That's used because it's often a proxy for the global metallicity. And so we often use it. We can't measure the global metallicity for all stars. It's really even difficult to measure for our own sun. How do we measure the abundances of some really rare elements inside the suns? You can do many elements, but some are a challenge. So we use often, for other stars especially, we use iron to hydrogen as a proxy for that global metallicity. And roughly, we can convert between the metallicity of some star and its iron to hydrogen abundance. Stellar abundances often look like this. They often are color-coded, which I've done. I put that orange color coding in there, and also the approximate time direction. So this is from Bensby 2017. The colored points are solar neighborhood dwarf stars. And yeah, so the colored points are micro-lens dwarf stars in the Milky Way bulge, and the gray points behind, these are solar neighborhood dwarf stars. And I think I'm not going to go into, I don't want to discuss this diagram really. I just want to mention these are the sort of diagrams you might see, where we have iron to hydrogen on the x-axis. 0 is solar. If you have a star that has iron to hydrogen greater than 0, it's considered metal rich. Less than 0, it's metal poor. As an example, if you have a star that's iron to hydrogen -1, it's about 1/10 of the solar metallicity. Here on the y-axis, we have magnesium to iron. Magnesium is an important tracer of what we call alpha element enrichment. And so these stars, which I've highlighted with the arrow, these are what we call alpha enhanced, because they have a magnesium to iron ratio that's about, let's say it plateaus at about 0.4. So that's 2.5 times the solar magnesium to iron ratio. Okay, so this is really most of my introduction. There are a number of good textbooks on this subject, going back to Clayton, 1984, all the way through to more recent textbooks. Probably the one I would highlight the most from a nuclear physics point of view is Christian Iliadis's Nuclear Physics of Stars. Okay. I was planning on pausing the recording to have some water, so let me just do that. Okay, the next section is on basic stellar evolution. So let's continue. So to put together these lectures, I used quite a lot of material published in a review paper that I wrote with John Latanzio in 2014. Much of that material is still relevant, but I have updated slides in a few places where important. Okay, let's go back to the beginning in some sense about basic stellar evolution and consider how stars produce energy. Well, this comes from mass energy equivalent from Einstein's famous equation E = mc squared. We know that the mass, for example, if we consider hydrogen fusion, that the mass of 4 protons is slightly larger than the mass of 1 helium nuclei. The mass excess is converted into pure energy, and that essentially is the energy that will power stars. How much energy is released? Well, for hydrogen fusion, we have about 26 mega electron volts. Converting that into joules, it's only about 10 to the minus 12 joules, but the sun produces this amount of energy about 10 to the 38 times a second. So for all of you who think that the sun's just a boring star, it is in some sense, but it's also quite amazing when we consider these numbers. Generally, when we consider stellar evolution, we draw the change in a star's observed properties on what we call a Hertzsprung-Russell diagram. So this shows evolutionary tracks as a function of surface temperature and luminosity. Now, for those who haven't seen this before, we have log 10 of surface temperature on the x-axis. We have log 10 of luminosity on the y-axis. And you'll notice that temperature goes the wrong way. So as you head to the left, the temperature is increasing, and as you head toward the right, the temperature goes down. So the coolest stars are found on the right of the diagram, and the hottest stars are found on the left of the diagram. So in this diagram, I've shown the evolutionary tracks. These are theoretical model tracks for 2 stars of 1 solar mass and 5 solar mass, both of solar composition. And here we can see, and then we've color-coded by various important phases of the star's life. We have the main sequence, which is where our sun is now. Our 1 solar mass star will spend 10 billion years here. Our 5 solar mass, only 100. After the main sequence, the core contracts. So you have hydrogen burning in the core right now. The star will eventually run out of hydrogen. When it does so, the core will contract, the outer layers expand, and the star becomes a giant for the first time. Stars in this phase of evolution are simply called just red giant branch stars. At some point, helium is ignited in the core, and the star goes through a phase of core helium burning. After helium is exhausted in the core, the carbon-oxygen core collapses, contracts, also then collapses, and we end up with then the star and the outer layers expand, and the star goes through a second giant branch phase, and this is known as the asymptotic giant branch. And this is roughly where our sun is today. Now, in this corner is where we find Mira-type variables. So these are AGB stars, and they're called Mira-type variables because they are experiencing long, large-scale radial pulsations. So they've got large extended envelopes, and the envelopes are radially pulsating with pulsation periods of a few hundred days usually. Now, this is just a brief recap of the types of burning chains that we'll find. This might be quite familiar to most of you, but if we consider from a nucleosynthesis point of view, essentially you start with pp chains. You have proton converting, essentially you have 4 protons converted into 1 helium nucleus. However, it does so via a number of steps. Essentially, we first build up deuterium. Deuterium makes helium-3. Helium-3 plus helium-4 then either branch out into what we call the pp2 or pp3 chains, depending on the temperature in the burning region. But the main result is essentially 4 protons. That 4 protons fuse into 1 helium nucleus, which releases energy plus other stuff, and that other stuff might be neutrinos and positrons, etc. Let's just, before I go on, from a nucleosynthesis point of view, probably one of the main features that's important is this buildup of helium-3. We also can produce lithium-7 via this pp chains, but it takes a special sequence of reactions, or special sequence of conditions more so that allow lithium-7 production to occur. Okay. The next sequence of reactions that produce energy are the CNO cycles. This is where carbon, nitrogen, and oxygen nuclei act as catalysts for hydrogen fusion. Here, the main energy-producing chain is carbon, is what we call the CN chain, or CNO1 here. This is where carbon-12 makes nitrogen-13, which quickly decays to carbon-13, that then also captures a proton to make nitrogen-14. This main chain, it produces most of the energy in stars on the main sequence, where CNO cycling is dominant in terms of energy production. Now, I don't really discuss the difference between the two, but generally stars less than about 1.2 solar mass on the main sequence, proton-proton chains dominate energy production. Stars over about 1.2 solar mass on the main sequence, CNO cycling dominates energy production. Doesn't mean, of course, that PP chains don't occur in a 1.5 solar mass star. They do. They just don't produce most of the energy. Likewise, CNO cycling is occurring in our own sun. It just doesn't produce most of the energy. Now, one of the consequences of CNO cycling is that the carbon plus nitrogen plus oxygen remains constant, or at least the number of nuclei does. Why? Because we're mostly rearranging carbon, nitrogen, and oxygen nuclei into nitrogen-14. I included nitrogen there because nitrogen-15 mostly gets burnt through P alpha to carbon-12, and that then makes nitrogen-14. CNO equilibrium ratios. Here I've put the ratios at the surface of the sun relative to the CNO equilibrium. And you can see that, again, we've taken, so the surface of the sun is dominated by oxygen-16. As a result of CNO cycling, we're converting almost all of that oxygen and carbon into nitrogen-14. We also find that the C12-C13 ratio, which we can measure in stars, it's one of the few isotopes that's measurable in many stars. And we notice that from CNO cycling that it goes from 90, which is observed at the surface of the sun, down to about 3 from CNO equilibrium. So this tells us, first of all, that if we see low carbon-12, carbon-13 ratios, say less than 30, at the surface of a star, this is an indication that the material that we see was exposed to CNO cycling. So it's, I guess you could say, a diagnostic of stellar evolution. There are also advanced hydrogen burning chains. This is an example of the neon, should be neon sodium, not neon neon, neon sodium on the left-hand side, and magnesium aluminium on the right-hand side. There are also higher order chains involving silicon and potassium and all sorts of things. Now, these chains, the left-hand side mostly converts neon isotopes into sodium, that is sodium-23. Through the magnesium aluminium chain, we essentially convert magnesium isotopes into aluminium. This is also a pathway to make aluminium-26. It's the main pathway, in fact, to make aluminium-26 in the galaxy. And we know there's quite a lot of live aluminium-26. It has a half-life of about 700,000 years out there, and it's mostly made through this process. Now, one of the consequences of these advanced burning chains, again, these are catalytic chains. You're rearranging essentially neon isotopes into sodium. Is that proton captures onto these isotopes because you have a larger nucleus involved, you need higher temperatures, but because they're catalytic, you're not making fresh. The total number of neon plus sodium isotopes remains constant, so you're not making any fresh stuff basically from this, you're just rearranging. Now, we've had a star that's gone through cold core hydrogen fusion and might have done any of those reactions I mentioned before. At the end of the hydrogen burning phase, it ends up with a structure that looks like my diagram on the right-hand side. It has an inert helium core that is contracting and heating. It has a shell of hydrogen burning around that core, and it has an envelope that is expanding. I've put some typical radii and also some luminosities and temperatures as we might find in a detailed stellar model. So this expansion along the first from the main sequence to the base of the red giant branch causes mixing. And what do I mean by that? Well, we have a star that, let's say you take a star like our sun. At the moment, it has a very thin convective layer, but as that outer envelope expands, it becomes more opaque, and we have convection developing in regions that weren't convective before. So this means that if that convection can get deep enough, that means the star's expanded enough. If it can get deep enough, it may reach regions of the star that was partially processed or perhaps fully processed by hydrogen burning reactions on the main sequence. And this is known as, so we have a star that's expanded, regions that had maybe some partial processing they expand enough that they cool, they become convective, they become part of the convective envelope. And if they've had partial processing, let's say you've converted, you have a region where you've made some carbon-13 in the outer layers, in the outer part of the core, that carbon-13 pocket might get mixed into the convective envelope. And this is known as the first dredgeup. We also have a second dredgeup. I won't discuss this quite as much, but this takes place after core helium burning, and it only changes the composition of more massive stars over 4 solar mass. First dredgeup we think takes place in all stellar masses, certainly for the mass range I'm talking about here. And we think it takes place when the star first ascends the giant branch, so at the base of that first giant branch. And we'll talk about that later. So this is really just putting into words what I've just said. So you can read this in your own time. You can pause the recording, you can have a read. Essentially, the outer layers expand and cool. As the material is less ionized, there are more ways for photons to interact with matter, so opacity increases, convection grows deeper into the star, so that thin convective, I'm going to try and do it on the video, that really thin convective layer starts moving inwards, you have more of the star become convective, and this is what we call a dredge-up phase, essentially. So what do we see at the stellar surface? So I mentioned carbon-12, carbon-13. This is a ratio that we can measure in the surface of stars through stellar spectroscopy. In the surface of our sun, it's about 90, and we want to know what we predict from theoretical models. So just to note that the isotopic ratios I'm plotting on the right-hand side, these are by number, so they're not mass, they're not by mass. And I've just given you an example of how to convert from one to the other. Okay, so if you look at the carbon-12, carbon-13 ratio, that's predicted from stellar models that range from 1 to 8 solar masses, you can see that you drop from 90 down to about 20. And so this tells us again, so what's happening? If the carbon-12, carbon-13 ratio is going down, that means we're mixing material that's been exposed to CN cycling into the stellar envelope where we see it at the surface. And this is indeed what's happening here. Same with nitrogen 14, 15. So I took here the initial proto-solar value ratio around 470. And as a result of first dredge-up mixing, you notice that that ratio goes from roughly 470 and it increases by almost an order of magnitude in some cases, at least by a factor of a lot, up to a factor of 6. Again, what's happening here is that, well, two things. We are destroying the first dredge-up so the base of the convective envelope is reaching a region of the star where nitrogen 15 has been destroyed. So that's the first thing. And the second, it's reaching a region where nitrogen 14 has been produced as a result of CNO cycle reactions. And if you have, so the two things, nitrogen 15 goes down, nitrogen 14 is increased, and the overall ratio just really increases by a considerable amount. Just a summary from first dredge-up. So this is the first thing that changes the composition of a low and intermediate mass star's life. The rough summary is that we see reductions in lithium. Lithium goes down, we'll try and show it like that. C12, C13 goes down. We see increases in helium-3 and nitrogen. Oxygen isotopes, there's not much change usually. Maybe we see increases in oxygen 18, maybe increases in oxygen 17, oxygen 16, we don't predict to change greatly. from first dredge up. However, the main summary is we're seeing the results of PP chains and CNO cycle mixed to the stellar surface. The depth of first dredge up and second dredge up really depend on the initial mass of the star as well as their metallicity. This is a diagram that I made for my PhD thesis. Now it's quite old, very much based on a similar diagram that was published by Boothroyd and Sackman in 1999. So I definitely recommend you have a look at their paper if you're interested in this topic. So you see first dredge up. So the solid lines are first dredge up, how deep it gets. And this is the depth that the convective envelope reaches compared to the total initial mass of the star. So you see that it reaches a maximum depth at around 2.5 solar masses. And you notice that a 6 solar mass star has much less efficient first dredge up, if you like, compared to a star of, say, 2 solar masses. However, the dashed lines show the depth of second dredge up and how much deeper it gets. So you see, for example, a 2 solar mass star, first dredge up reaches much deeper than second. So second doesn't change the surface composition. Whereas by the time you get to, say, 6 solar masses, second dredge up results in the largest changes to the surface composition before the AGB, before the thermally pulsing AGB. Okay. What effect does this have overall on the yields? Well, in terms of the S process, none. However, the first dredge up changes the surface composition, but the overall effect on even the global stellar yields, and by global I mean because the stellar yield is the total amount, this is the mass lost through winds integrated over the whole stellar lifetime. So if we look at the effect of first dredge up on the stellar yields, it tends to be fairly small, except for a few key isotopes such as maybe helium-3, carbon-13, and maybe some of the oxygen isotopes such as oxygen-17, but that's it. If the star experiences strong nucleosynthesis on the thermally pulsing asymptotic giant branch phase, that will overwhelm any change we've seen through first dredge up. However, there are a mass range, so less than roughly 1.2 solar mass, that we don't predict, although there's uncertainties there too, but roughly don't predict. We don't expect they'll become S process rich. So for these stars, first dredge up will dominate their stellar yields, so what they're putting out into the interstellar medium. What about comparisons to observations? Well, for stars over about 2 solar masses, we think that the predictions that I'm showing you here, so this is again carbon-12, carbon-13, match the observations pretty well. For lower mass stars, less than about 2 solar mass, the predictions don't match the observations so well at all. So I've highlighted the region where we have the predicted range, so roughly 20 to about 30 in terms of carbon-12, carbon-13. The observational range is below 20. So most low mass giants in the field, and that just means they're random stars in our galaxy, or in open clusters or globular clusters, so these are in star clusters, these show carbon-12, carbon-13 ratios much less than 20. By the time you get to metal poor clusters, globular clusters, they might have ratios of the order of around 3, 4, 5, 6, so close to equilibrium. So this tells us that these stars have experienced more CN cycling than what we predict from first dredge up. So what's going on? This has been motivation in recent years. I've just put a whole lot of references here. I don't have time to go into the details for what we call, it's just been labeled extra mixing, deep mixing, something that is not non-canonical, slow mixing that takes place in the envelope of low mass giants. This is it's a way of mixing products of the CN cycle to the stellar surface. We think it's done in a slow way, takes place after first dredge up. It results in further reductions to C12, C13, and carbon and nitrogen. Lithium may be destroyed or it may be produced. The mechanism, well, it's unlikely to be stellar rotation. In recent years, it's been favoured something called thermohaline mixing, which came from the oceanography, and it's essentially where you have in the ocean you have warm salty fingers on top of cooler, less salty water, So thermohaline mixing is where you have warm salty fingers on cooler water, but it might also be, but in terms of stellar environment, it's where you have, for example, inversions in the mean molecular weight. Now, the mean molecular weight is the mean mass per particle in the gas. So if you have a region that's where you have a lot of helium-3, the mean molecular weight in that region, which will be on top of above the hydrogen shell somewhere, that might have a higher mean molecular weight than material around it. And that can lead to the same sort of mixing processes we see in oceans. The issue with thermohaline mixing in recent times is it still depends on parameters. It's a 3D phenomena that's been compressed into 1D stellar evolution models. So it's we still aren't sure yet if how efficient it really is in stellar environments. It likely happens, but how efficient it is, we think there's still work to be done there. But I'm showing results from Charbonnel and Zahn from a couple of years, quite a few years ago now, showing log of luminosity. So as we move from 0 to 3, you're evolving from the base of the giant branch to the tip of the giant branch for varying quantities. Now, if you focus on carbon-12, carbon-13, you can see that you go from about 90, then it drops down to about 30, and then because of this thermohaline mixing, then that drops down even further depending on the mass of the model. Okay, what is the overall effect of this extra mixing on the stellar yields? Well, S-process none. In terms of others, there might be a few changes. If extra mixing is quite efficient, it might have a big effect on helium-3, on the yields of helium-3. In fact, it'll basically destroy all of it in the stellar envelope. Lithium reduction, production, the details depend on numerical details of stellar codes, and it still hasn't really been sorted out, I don't think, yet. Carbon-12, carbon-13, well, carbon abundance will go down, carbon-13 abundance will go up. Same with nitrogen-14, 15, nitrogen goes up, and nitrogen-14 in particular goes up, but the nitrogen-15, or probably a bit down. Oxygen isotopes, it's unclear how important extra mixing is. It may be, in a few cases, quite important, but I think if you're interested, I put a lot of references here, so I recommend you go have a read and try and learn a bit more about this. Okay, so moving on, we've reached the tip of the red giant branch phase now. So this is for stars less than 2 solar masses. We have an electron degenerate inert helium core that reaches temperatures of 100 million degrees Kelvin, and helium reactions, the triple alpha reactions, are ignited. Because of electron degeneracy, the core ignites. It goes through a thermonuclear instability. Essentially, what happens is that the gas is electron degenerate, doesn't react to changes in temperature, so the energy production goes up. But a normal gas, if you heat it, it expands. Electron degenerate gas doesn't do that, so it keeps on contracting. The temperature just keeps on going up, and the rate of energy production from the triple alpha, it scales with temperature to the power of about 30 or 40. So it's a huge increase in energy. And so this leads to something called the core helium flash. In more massive stars, over about 2, helium ignition in the core happens smoothly. So there's no electron degeneracy. The temperature reaches 100 million degrees in a normal gas environment, not electron degenerate, and the star goes through a phase of core helium burning. Helium burns into carbon-12 via the triple alpha reaction. This is really a 3-step process that's been summarized in that one single reaction. Helium can also fuse with carbon-12. This is a carbon-12 alpha gamma reaction. There'll be a lot of talks about this at Nuclei in the Cosmos, likely. Over time, we have, so helium decreases and carbon increases, something like this. Helium goes down, carbon-12 goes up, but at some point, carbon decreases and oxygen starts to increase. So maybe something like this. So the final carbon to oxygen ratio in the core of the star depends essentially on the rate of the carbon-12 plus alpha reaction, this carbon-12 alpha-gamma reaction. This is really saying in words what I've said previously on some of the slides, more or less, that at the end of core helium burning, the composition of the core is roughly 50-50, carbon-12, oxygen-16, but the final value depends, first of all, on the rates, so carbon-12 alpha-gamma, and can be as extreme as 10% carbon and 90% oxygen, depending on the rate of the carbon-12 alpha-gamma reaction. And I've already mentioned that there's a very steep temperature dependence of the triple alpha rate, and it's roughly energy production is proportional to T to the 40. That means that helium burning always leads to a very steep temperature gradient. This means the main consequence of this for stellar evolution and structure is convection. So a helium burning region is always convective, regardless of whether it's in a core or a shell. And that leads me to the AGB phase. So we have our star gone through a phase of core helium burning. It has exhausted its supply of helium and it has a carbon-oxygen core. This carbon-oxygen core contracts, the outer layers expand, and the star evolves up the second giant branch, which is also known as the asymptotic giant branch. We have structural changes. So at the end of the main sequence, a hydrogen-burning shell is established around the inert helium core. In this phase, we have a helium-burning shell established around the contracting CO core. And this helium-burning shell narrows as the star evolves. Eventually, the helium shell becomes thin and partially electron degenerate. Helium burning is unstable under such conditions, and this leads to thermal pulses or helium shell instabilities. However, the early part of the AGB is the longest in time, and this is where the second mixing event occurs. So just to give you an indication of the timescales, let's say a star spends 20 million years on the AGB. In total, it might be only 1 million of those will be in the thermally pulsing phase. 1 or 2 million will be in the thermally pulsing phase. Okay, so we've looked at where mixing occurs. We've had first dredge-up. I'm going to briefly mention second dredge-up, and then we'll focus on the final mixing phases. Now, I mentioned that second dredge-up doesn't get as deep as first dredge-up. Let's have a look at this in some real stellar models. They're not real stars, real stellar models. These are both we have a 1 solar mass and 5 solar mass star, both of solar composition. The x-axis shows time increasing on in both cases. You notice the hugely different timescales. And the y-axis shows a mass of the hydrogen exhausted core, essentially, for the two different models. Now, what we can see here is that the black line, let's just focus on the black line, black solid line, and this is the base of the convective envelope as a function of time in these two respective models. You notice how with the 1 solar mass, that black line reached a minimum at about 1.19 times 10 to the 10 years. This is first dredge-up. Notice that if you look at the very right-hand edge where that black line is, that's second dredge-up in our 1 solar mass star. Go to the 5 solar mass panel, and you notice that there is a minimum. This is at about maybe 8.3 times 10 to the 7 years. This is first dredge-up. This is on the left-hand side of the 5 solar mass panel, and then go to the very right-hand side of that image, and this is where we have second dredge-up take place. Notice how much deeper this gets compared to the first dredge-up. 5 solar mass, and so the 5 solar mass will experience larger changes to its surface composition as a result of second dredge-up. The main result, again, you're mixing material that was burnt during the preceding main sequence. So still hydrogen fusion reaction products, but this time it's going much deeper in, and you're mixing material that's been exposed to complete hydrogen fusion reactions. So you produce a lot of nitrogen-14. Indeed. This is from first dredge-up from before. Let's add in second. And you notice now we have this huge increase in the nitrogen-14 to 15 ratio in the stars that experience second dredge-up. So these are stars over about 4 solar masses at solar metallicity. So second dredge-up mostly affects nitrogen 14 and 15, And it also, because it's also mixing into a region where you've had complete hydrogen fusion, it also reaches into a region where there's considerably more helium as well. So the most extreme of these of the mass range, the 7 to 8s, they might have helium increases of, say, maybe 0.1 in terms of their mass fraction, which is just from the second dredge up alone. Okay, so that takes us now to the structure at the end of the early AGB phase. We have a CO core that was the result of core helium burning previously on the main that occurred previously, and now we have 2 burning shells. So this schematic diagram shows what our schematic structure of our AGB star looks like. So we have our hydrogen exhausted core where we have 2 burning shells, and this is all surrounded by our deep convective envelope that's still primarily hydrogen. Now, I mentioned that the helium burning shell is unstable and this causes mixing. So the main reason why AGB stars are important and why I focus on them and why they're really important for the story of the S process is because in that helium burning shell, that's where S process element production takes place, where a lot of nucleosynthesis occurs, and then they experience mixing between that hydrogen exhausted core and the envelope. And that mixing occurs periodically on the thermally pulsing phase. So if you have periodic mixing followed by rapid episodic mass loss, these stars also are observed to be losing really clumpy, dense outflows of material. And that is a way of moving material into the interstellar medium. Now, just to give you some indication of the mass and radial scales, let's say this is a 3 solar mass star. You might have, say, 0.6 solar mass in this hydrogen exhausted core, and about 2.5 solar mass, maybe in 2.4 solar mass in the envelope. In terms of the radial scale, let's scale the core, our hydrogen exhausted core, to be about the size of a marble, so a couple of centimetres across. To get to the outer layers of this star, I would have to go maybe 500 metres away. So that just shows you how centrally condensed these stars are. And everything we care about in terms of S process takes place in those surface layers of that marble, essentially. I quite like this movie. Let's just see if I can play it. This shows the radial pulsations that we see. All AGB stars experience these large-scale radial pulsations with periods of about a few hundred days. On the little inset shows where we see most of the wavelength, so where most of the light is emitted from these stars. And you see that as the stars become dustier, as they are losing more mass, that the peak wavelength moves from the infrared into the mid-infrared and eventually all the way through to the far infrared. So these stars are dusty, cool, essentially red infrared objects. They don't emit much visible light, and most of what we see about them is really in that, in order to find AGB stars, infrared surveys are the best way. Eventually they lose their outer layers. The core of the star becomes exposed, and that will illuminate the material lost, and we might end up with a planetary nebula, something like this. Okay, the final mixing is what we call third dredge-up. It's badly named, it occurs many times, and also something called hot bottom burning, and I'll focus on both of these. And this will be the end, and then final part of a couple slides on super AGB stars, and that'll be take me through to the end of first lecture. Okay, so what are the products of nucleosynthesis? I've discussed first dredge-up. This is the products of partial hydrogen fusion. Second dredge-up, the products again of hydrogen fusion. Now we're moving into the AGB phase, thermally pulsing AGB phase, where we have third dredge-up. This brings mostly the products of helium burning to the stellar surface, as well as neutron capture nucleosynthesis. And then we have hot bottom burning, and this is also similar to previous products of hydrogen burning as well. Schematically, this is a schematic Kippenhahn diagram showing time on the x-axis versus mass, so that we have, we're zooming in on the core. So remember those thin layers of that marble that I discussed before. So we have the CO core shown in yellow. We have the bluish, violet region, depending on what colors you see, In the inner, this is our intershell, our helium-rich intershell zone. So this is, if you like, is the ashes of hydrogen fusion, hydrogen burning. And then you have a hydrogen shell at the base of the convective envelope, and then the outer convective envelope. This is mostly hydrogen. We have a convective thermal pulse. Now, remember that I said helium fusion always results in convection. So you have helium ignited at the base of the helium shell. It drives convection. That leads to structural changes, essentially causes an expansion from the middle of the shell outwards. That expansion leads to dredgeup, mixing. Following dredgeup, the star recontracts and hydrogen shell is reignited and the star continues on its way. And then we might have this phase of helium shell ignition, followed by expansion, followed by mixing, third dredgeup, and then recontraction. That might occur many times on the asymptotic giant branch. But the main consequences are, and this is probably one of the main things I really want you to take away, is that we have nucleosynthesis in the helium shell, and we have repeated mixing events that mix those products to the stellar surface. And then you have mass loss that removes this into the interstellar medium. Finally, we have something called envelope burning or hot bottom burning. They're the same thing, where the base of that convective envelope might become hot enough to sustain proton capture nucleosynthesis. Now, this is because the envelope is very well mixed. There's no mixing event needed. The envelope is by a definition convective, and even if it's quite turbulent, it's very well mixed. You have a convective turnover time, maybe of 1 year. So that means any nucleosynthesis that occurs at the base of that envelope is seen quickly at the stellar surface. All right, I mentioned helium shell instabilities. This is essentially where where the helium shell thins, and it is the thin shell instability that causes thermal pulses to occur. Essentially, it's not caused by electron degeneracy like the core helium flash. This is caused by we have a contracting shell. It becomes thinner, becomes hotter. You have energy. The temperature increases well above 10 to the 8 kelvins. That leads to the triple alpha production, producing energy, but the shell cannot expand enough to cool. And that means that the temperature just keeps on going up and the energy production keeps on going up until eventually it does expand. At some stage, it leads to a thermal runaway, but eventually at some stage it produces enough energy that it causes essentially a mechanical expansion of the star. So the energy doesn't reach the stellar surface, it's converted into mechanical energy, and it physically expands the whole star, not just the shell. And that shuts off the thermal pulse. This thermal runaway can produce luminosities of up to 10 to the 8 solar luminosities, 100 million solar luminosities per thermal pulse, perhaps. Let me show you an example. This is a 2 solar mass model of solar composition. I've plotted here as a function of time, log 10 of the helium shell luminosity in black and the radiated, or essentially the stellar luminosity, in red. And notice the stellar luminosity, it does vary. It goes through, so it goes up, down, up, down, up, down, factor of 2 change. But you notice that the helium shell luminosity varies by many orders of magnitude as a result of thermal pulses. And this star itself might have 20 or so thermal pulses that are evident in this figure. This just shows schematically, sort of graphically, in a very poor person's graphics, what the thermal pulse cycle might look like. So here I've now note this is definitely not to scale. So we have a carbon oxygen core, helium burning shell. Red is indicating it's on, producing a lot of energy. Helium intershell zone, hydrogen shell, where the pink indicates it's producing a lot of energy. Then we have a deep convective envelope. This is where the helium shell drives intershell convection. Eventually, the whole star expands, the thermal pulse is shut off, and intershell convection starts to retreat. The whole star is being pushed out, and the hydrogen shell is extinguished, it goes out. So the temperature is being pushed out to a region that's much cooler, and it's shut off. That allows the convective envelope to move inwards in mass, and this is third dredgeup. And this is how we get S-process elements to the surface. The star will recontract and the hydrogen shell reignites and will provide most of the star's luminosity for the next maybe 10 to the 4 years, depending on the core mass. And then the star recontracts, hydrogen shell provides luminosity until the mass in the helium shell builds up again, and then the helium shell will ignite. And this process can occur many times. So this is in words what I've just said, so feel free to pause it and read this through at your own time. The main thing I really just want you to take away is that you have a thermal pulse, helium shell burning. Timescales are roughly 10 to the 2 years. That leads to mixing, third dredgeup. Again, 10 to the 2 years, and that's followed by a longer interpulse phase, maybe 10 to the 5, 10 to the 4 years, depending on core mass. Okay, so what are the consequences of third dredgeup? Well, as I mentioned, it's badly named. It can occur after each thermal pulse. This inward movement of convection reaches region that has experienced partial or maybe complete helium burning. That means we're mixing, and what is the main product? That's carbon-12. So we're mixing, and this is carbon that's been made from the hydrogen and helium initially present. So it's fresh carbon. This is not carbon the star was born with. So each third dredgeup mixing event will mix fresh carbon from the helium shell into the stellar envelope. Now in this model here, this is a mass, it's a 1.8 solar mass model, Z of just a bit less than solar. It's a typical galactic carbon-rich AGB star mass. And if you focus on the right-hand panel, we can see the mass. This is essentially a Kippenhahn diagram. This is the CO core increasing with each thermal pulse. And then we see the red line shows the base. So this actually shows the mass of the hydrogen exhausted core change. And each time it goes down, and it looks very sharp. It's only sharp because of the difference in timescales. Each time it goes down, we have a third dredgeup event. Some carbon is being mixed from the core into the envelope. And this will increase the carbon to oxygen ratio. We also have, so it's not just carbon that is made through helium shell burning. Helium burning occurs in the ashes of hydrogen burning. This composition is typically 98% helium, but 2% nitrogen-14. That nitrogen-14 can suffer alpha capture twice to make neon-22. If the helium shell is hot enough, so maybe more than 300 million degrees Kelvin, neon-22 itself can suffer alpha capture to make magnesium-25 and 26 with almost equal probability. So these reactions produce not much energy, but they're really important for nucleosynthesis. Also, we can make fluorine. I didn't want to go into fluorine because there's a really long chain of complex reactions. If you're interested, I can provide some references. Now, these reactions are important because not only do they result in important nucleosynthesis, but reactions such as neon-22 alpha N makes neutrons. So this is a source of free neutrons in the helium shell. And this is one of the main neutron-producing reactions in AGB stars. What do we see at the surface? This is results for a 3 solar mass model of solar composition. On the left, I'm plotting as a function of thermal pulse number. Think of this as a proxy for time versus the C/O ratio that's at the surface of this stellar model. So I put the line for C/O greater than 1. So when the star crosses this line, this model would be seen as being carbon-rich. So it has a carbon-rich atmosphere. Note our sun and most stars are oxygen-rich, where the number of oxygen atoms exceeds the number of carbon atoms. Right-hand side, we see fluorine, and you see the fluorine abundance increases by an order of magnitude almost. So this is a way of making carbon-rich, fluorine-rich stars. We observe carbon stars in our galaxy and other galaxies. The mass range of carbon stars is predicted to vary greatly with metallicity. This is a plot showing as a function of initial mass, the C/O final C/O ratio predicted from the stellar models. And we can see that for solar metallicity, as an example, these are the pink squares. We see the mass range for carbon star production is roughly 2 to about 4.5 solar masses. So this gives us a prediction which we can compare to observations. One caveat, of course, and I'll get into this probably in the next lecture, is that it's quite difficult to determine masses for real stars in the galaxy. Gaia is helping a lot here, but it's still a problematic. It's still a problem. It's still a problematic thing to do. Okay, the final thing I wanted to discuss in terms of AGB stars is hot bottom burning. It's I guess a colourful name given to another burning process that occurs at the base of the convective envelope when it reaches temperatures hot enough to sustain proton capture nucleosynthesis through CNO cycling, neon sodium chain, magnesium aluminium as an example. Now, these stars have second dredgeup, so we result in large changes in helium abundance, and then they may also have third dredgeup, but then they can also have this extra burning process called envelope burning or hot bottom burning. Now, this is a 6 solar mass of solar composition, old solar. Anyway, it doesn't really matter for our purposes. This is time on the x-axis versus the temperature at the base of the envelope. And you can see that the base of the envelope is periodically getting up to about almost 80 million degrees. Notice the change, how it's going up and down. That's because of expansion. Each time you have a thermal pulse, the whole star is expanding. So that pushes the base of the envelope into cooler regions. So the temperature goes down. Then the star recontracts and the base of the envelope goes up again, and hot bottom burning reignites. So this is why we get that up and down sequence in this diagram. On the right-hand side, I'm showing as a function of scaled time. I think I scaled it to maybe second dredgeup, doesn't really matter, where we can see this is log of abundance in terms of abundance by number for some CNO nuclei. And in this 6 solar mass model, you can see oxygen is unchanged, nitrogen is going up, and carbon-12 and carbon-13 are close to equilibrium. Now, you might be saying, this is almost 80 million degrees Kelvin. Why is oxygen-16 not changing? Good question. I hear you ask. Well, that's mostly because the base of the envelope is not as dense as a regular hydrogen burning environment. The centre of our sun might be 160 grams per cubic centimetre. The base of a convective envelope might only be a few grams per cubic centimetre. So this is one, I guess, place in a stellar environment where density plays an important role at regulating the rate of energy production and also the rate of thermonuclear reactions. Hot bottom burning and third dredgeup may or may not happen. I don't know why that line is where it is. That doesn't really matter. I think I was trying to show the maybe the equilibrium line. Anyway, it doesn't really matter for the purposes. It shows C12C13 at the surface as a function of thermal pulse number on the left-hand side. And we see the C, and on the right-hand side, we see the surface carbon to oxygen ratio. Again, these abundances by number. And you notice that the C to O ratio in this 6 solar mass model, it never exceeds unity. So it never becomes what we call carbon rich. Now, third dredgeup still happening though. So does it make S-process elements? Good question. We'll get to that in the next lecture. Finally, I mentioned that lithium production may occur as a result of the PP chains. Now, normally you produce lithium through the electron capture of beryllium-7. So we make beryllium-7. So helium-3 captures an alpha particle, helium nucleus, that makes beryllium-7. Beryllium-7 beta decays to lithium-7 or electron capture, makes lithium-7. But what happens to that lithium? Normally, lithium captures a proton and is destroyed away again to make helium-4. But what if I have PP chain plus convection? What if I can make beryllium-7 at the base of the convective envelope, but then transport that beryllium-7 away before it or lithium is destroyed again? This is one way where I can essentially make lithium-7 in a stellar environment. So we need to have this combination of PP chain plus convection, and this happens at the base of the convective envelope of intermediate mass AGB stars through hot bottom burning. This shows the results of this is called the Cameron-Fowler mechanism, where beryllium-7 is transported by convection, where it captures an electron to produce lithium-7. That lithium-7 stays at the stellar surface for some time, eventually goes down again, is destroyed, but then you make fresh lithium-7, goes up again, and it's in sort of in an equilibrium. Some stage, though, you run out of helium-3. Because remember, all of this depends on the amount of helium-3 you have. You run out of helium-3, and then the lithium you've made goes down, and At this point is when most of the star's mass is lost. So this means that this six solar mass star, for example, it's overall not a net producer of lithium in galaxies, even though it is lithium rich. In fact, it's what we call lithium super rich. It's super rich in lithium for about 100,000 years of its life. Overall, it will, when it dies, overall, it is most of that lithium that it made, it was all destroyed away again. So it doesn't really contribute to the chemical evolution of lithium in galaxies. All right, so just to summarize what we find for AGB stars of various masses, and I've sort of summarized the situation for stars close to solar metallicity, that for stars between about 1.5 to 4.5, these stars become carbon rich, they experience the dredge-up, they become rich in S-process elements and fluorine and neon-22, etc. Stars less than about 1.5 probably only have first dredge-up. They are not predicted to have any of this, to have any third dredge-up. They're not predicted to become carbon rich. Stars greater than about 4.5 solar mass, they have third dredge-up, they have hot bottom burning, but hot bottom burning is so efficient that it destroys any carbon that you make. It converts it to nitrogen and the C/O ratio stays less than 1. So these remain oxygen rich for most of their life. They can become carbon rich, that's a caveat at the very end. So it's important to note, I'm not discussing AGB modelling uncertainties, and I've mentioned a few of them, I've mentioned them here and there. I'm not going into details. If you're really interested, I suggest there's a lot of reading on this topic, and especially about these mass ranges, how they can shift. Recent new results are showing that there are low mass AGB stars in our galaxy of about 1 solar masses that are rich in S-process elements. They're even a little bit enriched in carbon. So maybe these mass ranges, which are based on theoretical models, but they are motivated by observations, that maybe these need revising once the full results of Gaia Space Telescope are known. Okay, I'm only going to really briefly talk about 8 to 10 solar mass stars. They're really interesting. There's a really interesting mass range, but they're kind of super difficult to model. And do they make many S-process elements? Don't know, actually. I've given a summary of the history of these stars. There wasn't a lot of work. Really, they were discovered or worked on first by Ken Nomoto in the 80s and later by Iko Ibn and collaborators. It wasn't really until the early 2000s, mid-2000s, that a lot of detailed AGB models started to be made by Pilar Gil-Pons and later Lee and LCS. Now there's quite a few of these models because, you know, it's realised that they might have interesting fates, such as electron capture supernovae, and might do some interesting things. However, they're difficult. Why is that? They go through off-centre degenerate carbon ignition and at temperatures of maybe 800 million degrees Kelvin. So this shows a Kippenhahn diagram for one of Lee and LCS's models, where the convective zones are highlighted, where you have a carbon flash initially, that leads to a carbon flame that eventually takes carbon burning through to the centre. Then you have off-centre carbon burning throughout the rest of what's now an oxygen neon core. We still don't really know what fraction explode as supernovae or leave maybe massive oxygen neon white dwarfs. I've put a few references here. If they do not explode, they will evolve as what we call now super AGB stars. So they're like AGB stars, like regular AGB stars, but they're much more massive, they're much more luminous, and they would even be the brightest red supergiants in a fairly inner population. So they might look like red supergiants, they might not look like regular AGB stars. If they have stellar pulsations, they might look like AGB stars, that just especially bright AGB stars. We haven't specifically found any for sure, and that's simply not necessarily because they don't exist, but because the initial mass function, so the birth distribution of stars that I mentioned near the beginning of this lecture, it doesn't favour them. It's predicted to be many of them in any given stellar population. Okay, what is the fate? It's uncertain. We think that some fraction will produce massive oxygen neon white dwarfs. Some fraction may explode as electron capture supernovae, but we don't know what that fraction is. What are their nucleosynthesis products? Well, we think that if they go through this super AGB phase, they experience very hot bottom burning. We don't know how efficient the dredgeup is in these stars. We don't know if they make S-process elements. We think that many of them are likely in binary systems, so binary evolution is likely to be really important for these objects. How do they affect the enrichment of the galaxy? Still a lot of open questions relating to this mass range. There's a fairly recentish review by Carolyn Doherty from 2017, and I recommend you have a look at that paper if you're interested in these objects. I put a diagram from one of Carolyn's papers on the right-hand side, showing initial mass as a function of metallicity and showing what the various fates are and the mass ranges, noting that the mass range for electron capture supernova, that is ECCN, is really uncertain. It depends on the numerical choices within the code you use to calculate these sort of models. Okay, that's it for lecture 1. Next will be about the S process, and then we will continue this discussion and we'll put what we've covered about AGB evolution and nucleosynthesis into the context of S process element production.